Okay, let's get started now. First, good morning, everyone. Welcome to our talk. And today, we're going to share some of our empirical experience of applied deep learning into one of the new security area called UEBA. First, a quick introduction of us and also the company. My name is Jixin Wang. And this is my colleague, Shirley Wu. We both joined Aruba, Hewlett-Packard enterprise company early this year through the NIARA acquisition. My previous experience mostly focused on applying state-of-the-art machine learning and big data into cybersecurity. And Shirley has been spending more than 1 decade of time building scalable big data infrastructure for different kinds of BIs. And NIARA actually is a 3.5-year-old startup which reinvented enterprise security using big data and machine learning. The new area we kind of worked with other vendors together is called User and Entity Behavior Analytics, aka UEBA, and the company was acquired early this year. Before we get to the details of those deep learning use case examples, I want to first spend some time explaining what UEBA is or what security problems we try to solve in this UEBA solution. These two graphs show us a clear security gap in the current enterprise security market. On the left, the enterprise security spending increased almost 100% in the last 5 years of the time. But on the contrary, you can see the number of the data breach for big enterprise these days increased even more than doubled during the same period of time. So, there's certainly a gap there. How did this happen? A couple reasons. First, attackers these days are really innovating and adapting very fast. Some of the attackers actually they are working also very hard, sometimes even harder than us. So on the other hand, also the traditional security defense strategy become less effective. Why I'm saying that? These days, especially with the increased user, most of the traditional security solutions, what they try to do here is to detect and prevent the bad guys from entering into the enterprise. But these days, with the increased use of IoT, cloud, this strategy just become less effective. The reason is because the border of the enterprise become more and more weak. I'll give you one example. Like say you bring your iPhone into a Starbucks, then you receive an email containing a phishing URL or malware URL. You click the URL, then your phone gets compromised. Then you bring your phone back to enterprise. In that case, all of the defense system, most of the big companies, they deploy on the border of the enterprise, it just becomes useless. The compromised entity is already inside the enterprise. So then what can we do in this case? Same thing, a couple things I think here. First thing is just similar to most of the consumer industry, we should take advantage of some advanced machine intelligence like deep learning when combating with the attackers. Second, we also need a mindset shift here. So for most of the big enterprise today, some of the user or devices being compromised is not a question of if, but a question of when. So when we design the new next generation security solution, enterprise security solution, we should just take this fact for granted. Some of the users or enterprise in your network is already compromised. Then the goal becomes like, how can we detect this kind of compromised user or device before they make further damage inside the enterprise? So you can see the mindset shift here from the outside attacker to the malicious insider. And to sum up here, for any of the UEBA solution, there are 3 key points. First, it should be driven by machine intelligence rather than just the human knowledge. Second, as I mentioned, it should not just focus on detecting attackers from outside, but it should also include those like compromised, especially malicious insiders inside the enterprise. And similarly, we also shift from this prevention-only solution to this kind of post-infection detection strategy now. And from our current customer experience, we have about 2 digits of the customer, different big, small customers. We have observed that at least there are 3 different security use cases or gaps this kind of UEBA solution can help to cover. The first is certainly the compromised user and device cases we talked about already. And most of the headline enterprise breach, you probably heard some like Target a couple years ago, Sony last year. All of this starts from one compromised device inside the enterprise. The second category is what we call the malicious insiders. And you probably have heard many cases these days, employee leaving the company by stealing large amount of the IP or company sensitive information. Actually, there's an interesting case we actually heard from one of our customers recently. So the company, our customer company, they announced some layoff plan for about like tens of employees. And the IT team noticed the access and the usage to their internal like code, document, different repositories increased almost 3x. But without any of this like a behavior monitoring or detection solution, they just have no visibility about what happened there. So I think this becomes more and more typical and the case and also the concern for different sizes of the enterprise. The third category is what we call the negligent users. Let me ask you a question. How many of you heard of the WannaCry ransomware last month? Any of you got compromised or been the victim? Send them the Bitcoin? Okay. So we're just lucky here, I think, but you probably heard of that outbreak. It compromised over 200,000 devices from over 100 countries. So this is a very typical negligent user case. Why I'm saying that is because Microsoft released the patch for that vulnerability actually a couple months before the outbreak. But the people these days are either just be too busy or too lazy to patch their system. So it's not with the increased use of the IoT devices or personal devices in the next few years, we expect this kind of knowledge gap or this thing will remain there still for quite some time. This is actually the main motivation to develop a UEBA solution. Now we understand what kind of the goal of a UEBA solution. I want to go a little bit deeper to explain a couple use cases we developed based on deep learning to detect the different kind of behavior anomalies there. There are actually 3 kind of attacking behavior we normally observe in the enterprise after attacker compromise the device there. The first, let's come back to this iPhone compromised iPhone case. Now you bring your phone back to your enterprise, but your phone most probably will not have a lot of the sensitive information. So in that case, the attacker will make your phone as a bot and then try to scan the whole intranet to find those high-value SF servers, right? So that is what we call the scanning attack as the first stage. Then after the attacker found those high-value SF server, which may have your IP, your code, whatever the sensitive information, the next step is to moving those data from those servers to those compromised machines. That's the second stage. It's the internal data download or sometimes called infiltration. Then the next stage, really at the end, they need to figure out some way to send the data out. It's called like data exfiltration. But even data exfiltration these days can be very tricky from those like well-designed target attack. Like one example we have seen in the real world is, most of the advanced attackers these days, they want to send a large amount of data. let's say 100 gigabytes in 1 minute, and especially or directly to the destination, especially the destination is in the foreign country. You know why? It's just because all these signals are so strong to be caught by even some simple heuristic-based solution. But what we observed is in one of the real-world attacks is when the attacker control a lot of or steal a lot of the internal data. What they first did is, certainly encrypt the data to avoid any of this just a pattern matching. Then they will chop the data into this small chunk of 10 megabytes, 100 megabytes, and then they slowly send the data out at a different pace, at a very slow pace. And also, since in that case, the attacker is from a foreign country, and they won't send data directly there because most of the company will just detect that kind of behavior. So what they did is actually they use Box or Dropbox, this kind of a local cloud service, as an intermediate. They first send the data to the cloud, and then they can fetch the data later from the cloud. So you can see this, for especially this kind of very sneaky behavior in the modern attack, none of the traditional heuristic or rule-based system can really catch up with them. That's actually the reason we developed this called this convolutional neural network-based behavior anomaly detection in our solution. So these two graphs shows two users' daily behavior inside the enterprise. Let me quickly explain how to read the graph here. So here, each of the subgraph represents a user's daily behavior over different protocols. And the y-axis of the subgraph represents 24 hours of the day, and the x-axis represents the 60 minutes of the hour. So in this way, each pixel of this subgraph represents 1 minute of the day. And the color of the pixel here just represents whatever the behavior, the quantity number of the behavior you want to monitor. For example, in this case, we monitor the user's data transfer behavior. And the more red the color, the more number of the bytes this user transferred through that protocol during that minute of the time. So here we show like two normal users in our company. And you can see this is a very typical user behavior. They come to office between 8 to 9 and they leave between like 4 to 5. But you can see there's still some difference here. This user 2 seems to like to have a lunch break, while user 1, as a comparison, works harder during the time. So from our current experience, this kind of multi-channel image encoding of the user daily behavior can be very discriminative to differentiate the different users, even in the big enterprise. Now let's take a look at how machine behavior looks like in this encoding. This is a machine I think it's some very low volume document server in our enterprise before in our company. And since machine is mostly programmed for some regular work, it's not very surprising you see this regularity in the machine behavior. They are just programmed to do some specific thing at some specific time, at each hour or different time of the day. Then, given all of with this kind of multi-channel image encoding, we actually build a convolutional neural network out from that. So during the training stage, we collect the past 90 days of all of the users' behavior image from your enterprise. Then these are the training data. This training data are labeled with the username, date, group, or different kind of user attribute information. Those images are fed into this neural network here. And here we just build 2 layers of the convolution and the pooling for the feature extraction. And also we expanded it to a fully connected graph here with 1,024 nodes. And at last, this is according to whatever Hinton's paper, you have to do some random dropout to avoid the overfitting in the system. So after the whole training process, we expect each node at this output layer represents a unique user in your enterprise. Then, with this, after we train this neural network, we can then take this to the next, the inference or the detection stage to detect any of the anomaly or deviation from that. So in the detection stage, we also convert each of the users, just to say we train with the last 90 days of data. Then we take, in the detection, like we take today's users' traffic and convert them into this multi-channel image, still feed into this, the pre-trained classifier, neural network. And if the output, if the light lit up here is share the same username with the image from the input, that just means that user does not change its behavior during that day of the time. It still follows the normal behavior range. But if it happen to light up a different node in the detection stage, that means the user changes behavior. It changes to the behavior of a different user in the enterprise. So this is kind of the computational graph we build for the training and the detection. And then now let's take a look of some real-world examples of how we detect those kind of behavior anomalies in different attack stages. So one example is this compromised user case. This is a normal user behavior, daily behavior graph we have seen before. And after this user is compromised, you notice there's a very intensive data transfer using a new protocol, FTP, which never used by user before, and at some after hour time. This user is a normal data work user. So not very surprisingly, you can expect the behavior model, the convolutional neural network can detect this kind of deviation and anomaly here. We can take another look of some IoT device example here. This is actually a job camera which is installed in our office. This job camera only does 3 things. Take videos all the time, encrypt the traffic, and send to AWS. So then you can look at the behavior of this job camera. It's very regular. Very intense encrypted traffic connection to AWS through SSL. This is the network time synchronization for that server. That's it. But after it's compromised, and it has been used for this internal scanning and data transfer, we started observing this intensive data transfer over a new protocol. This is just another example of how to detect this compromised device inside the enterprise. Yeah, I think so far we explained the one approach or one model we developed in our system. It looks very cool. But one doubt you may have in your mind now is how noisy this system is, right? It looks pretty cool to detect this, but how many, or in other words, how many of the false positive alerts generate from that? No, I can see from your smile, yes, you're right. This model actually is very noisy. This is a nature challenge for any of these human behavior classifier or detector. Human beings are not like machines which are programmed for the regular work. So in that case, human beings can change their behavior during whatever time of the day for even no reason. So to address this challenge, we have developed a couple solutions in our, a couple ways in our solution. First, we collect all different kind of, we collect over tens of different behavior logs to profile, to fingerprint each user in a very high dimensional space. For example, we collect the badge log to monitor the user's physical access to the building and the lab. Also, meanwhile, we also collect this called authentication log. This can help us monitor the user's behavior, remote access behavior to the servers. Certainly, we have all different logs covered, like the cloud usage, the SaaS usage, all different kind of behaviors. Then we use that convolutional neural network-based approach to detect the anomaly from each of these dimensions. So after we collect all tons of these false positive or true positive anomaly signals, the next step is to aggregate these anomaly signals from the same user over the temporal dimension or temporal space, and also check for some specific temporal sequence pattern before we make the final decision. So the idea here is if what we detect is a real attack, we can expect at least 2 things. First, we should observe more than one anomaly signals from that user. Second, most probably those anomaly signals from the same user should follow some kind of the temporal sequence. If you remember the three-stage attack I just introduced before, the scanning, the infiltration, and exfiltration. If you observe a user who has shown different kind of anomaly signals for each of these stages over time, and especially these signals actually follow some expected temporal sequence order, this can just increase our confidence of detecting a real attack. So since like in this case, we are profiling and detecting this temporal sequence, recurrent neural network is a pretty like native solution here. I will briefly introduce how we train this recurrent neural network now. So on the left side, these are just the list of the list of the events under the same user, from certain time window following some of the sequence here. It's just a sequence of the input events. And these are just the expected confidence level of detecting a real alert by observing different stages of this sequence. You can see, when you move to the later stage of this sequence, you also can increase the confidence level of this detection here. So this is just one example of the input data we take into the neural network. Then the first thing in the recurrent neural network is the input encoding. Here it's similar to most of the natural language processing approach. We take this called one-hot encoding, which means each of the unique anomaly types is represented by 1 bit in this input vector. Since we have about 200 different types of the anomaly signals, so we actually choose the vector size as 200 here. The difference I want to point out here is rather than just use the same weight 1 for each of the, in this one hot encoding, we actually also consider of the time interval between 2 consecutive events in the sequence. So the idea here is one example, like if you have seen 2 users showing the same 4 events in the same sequence, but whether these 4 events happen within 1 day of the time versus 1 week of the time, give us a different confidence of detecting a real alert. Generally speaking, it's like the shorter the time interval or time span of this sequence, the higher the confidence we're detecting a real alert in this case. So that's the reason actually you can see here with the weight of this one-hot encoding is actually a function from the function of the interval between 2 consecutive events here. So this shows a real example how the input encoding looks like. So you can see these are not 1 anymore. These are a floating number between 0 and 1. After we encode all of this event, the next thing is to build this recurrent neural network. Here we choose this called a long short-term memory. Probably most of you, if you work with RNN before, this is a very popular model people use. And we also set the history, the memory to the past 100 events in the sequence. And since the output score is expected to be an integer between 0 to 100, here after the output layer, we use a softmax here to convert the output layer to some probability distribution, and then use some maximum likelihood to pick 1 value out from that as our output confidence score. So after we train such a recurrent neural network, we expect, when we move to the detection stage or inference, we can feed it with any sequence of these different anomaly signals with different time information. And we expect the model will just automatically generate 1 confidence score out from that for different kind of sequence. So these are just the 2 different neural network examples we have developed in our system. And actually, in the real solution, we have developed pre-trained more than 100 different models, and a lot of them are just simple models like logistic regression and then naive-based models. And next, I'm going to hand it over to my colleague Shirley to introduce the big data infrastructure we have developed there. Or you can just.
Thanks, Jushin, for the introduction. So, so in the next few minutes, I'm going to go into our data infrastructure, how we build our data pipelines to support our UEBA solutions. So first of all, for analytics, every time we talk about analytics, the first thing is data. Where does the data come from? What type of data we'll collect to support our solution? So for us, since we're dealing with security network, so we collect the network packet data, which is live data, and also a variety of log sources. Currently, we support over 10 different log sources to cover different spectra of user behaviors. So the data we collected will go be streaming into our system. We use a mini batch streaming into our system. Why we do the mini batch streaming? The rationale is behind it is that after the data goes through the first initial stage to do the cleansing, pre-processing, we need to do the cross data source correlations. Since we are doing the UEBA solutions, user is a key properties in the data. But since we all know that for packets, network packets, you only have a source IPs, you don't have usernames. And the source IP can be assigned to a different user at a different time. So in order to identify who is the actual user who owns this IP and initiate those activities at a given time, we have to join the network data with the DHCP logs and AD, Active Directory security logs. In order to solve the problem of the data source synchronization issue, that's the reason why we use a mini batch based on different time bucket to do the data cross-batch correlation. So then after the cross-source correlation, Jishi mentioned earlier, we have over hundreds of machine learning models we trained offline. Some of them we're going to embed it into our ETL pipeline to do the real-time classification. Okay, so this is pretty much our ETL data pipeline. Next will be, data storage. We partially replicate our data into 3 data stores, HDFS, HBase, and Elasticsearch, to support multiple use cases for our solution, from backend to the user interface. So I'm going to focus on the Parquet. Parquet is a file system-based columnar storage. All our offline analytics, including the deep learning models, is working on top of the Parquet data. So this is a batch analytics. We are going to be primarily working off the Parquet data. So we have hundreds of machine learning models. Most of them we're going to start, first you get the Parquet data. We do the baseline profiling. And so you can load the historical data for each entity to build the baseline normal behavior patterns. And also, earlier we discussed about the entity encoding. You take the actual user data to encode into the image. That's going to be happen at here as well. So after you build the baseline and you get your model ready, then we do the normal detection for the incoming data and also future data to do the abnormal detection to capture the abnormal signals. And the risk scoring is another example we gave earlier that you have multiple abnormal signals. Then we can collect each user's abnormal signals and the time dimension to see the abnormal patterns to make the final detection. So this is our end-to-end data pipeline, structure. Of course, since we're a software vendor, we're going to need to deploy this architecture into the customer environment. So we currently support, on-premise, private cloud, or public cloud solutions. So we have our benchmark models based on the input data volume, how large how large volume of data we're going to consume, so we know how large the clusters is required to support this customer. So some of the small customers, only 3 nodes, barely enough to support the Hadoop cluster, but some of the large customers going to be 20 nodes. And of course, they're going to have a fourth options is that one of the insurance company, which is our customer, their IT, their hosts huge Hadoop clusters. So they want each one of the business applications, you only request the dedicated HDFS storage and the CPU resources. So this kind of a multi-tenancy deployment into the customer's cluster. So in this case, our application has to be for your deployment and upgrade, you cannot cause any downtimes at the cluster nodes. And also your upgrade deployment cannot impact any other business applications. So because of these restrictions, for our deployment strategies, our libraries and the source code primarily just reside on the edge nodes. And during the job submission, we can push our code to the cluster nodes. Of course, it's going to cause some overhead, but it's going to be another topic. So we have different techniques to maintain our worker environment on each cluster nodes. We can dynamically figure out, do I really need to reload the libraries from HDFS to rebuild a worker environment, or can just reuse of data and files on our worker environment to launch my job? So this is a different topic I'm happy to share after the presentation, okay? So, now we talk about our infrastructure and the deployment strategy. So you can wondering, hey, how the deep learning model fit into this picture? As far as you know, that deep learning is quite complicated. It's another beast, right? So for deep learning, we evaluate the different deep learning libraries from, from TensorFlow to Caffe and MLlib. Finally, we decided to go with TensorFlow for a variety of reasons. And so our data scientists will develop their model on their laptop, just standalone TensorFlow. But in the production or testing, we need to move this into the distributed TensorFlow so we can pump up the training data and also can save the training time. So as far as we know, in the distributed TensorFlow, typically people running distributed TensorFlow is on a separate cluster compared to the ETL and analytics clusters. But this is going to end up a cost for hardware cost, and also the complexity for the DevOps. And also we have to transfer the data from the ETL analytics cluster to a training cluster in order to do the training. This is going to end up a lot of overhead and data delays. So, but we want to go with TensorFlow, but we don't like the distributed TensorFlow, this type of architecture. What we did is we utilized Yahoo's open source project. They call it TensorFlow on Spark, which embed the TensorFlow, distributed TensorFlow into each one of the Spark executor. So what does it mean that, at the end of the day, your TensorFlow training job just is like a Spark job. So from a Spark command line, you can just launch your Spark job. And based on your, on the command is the additional parameters to define your distributed TensorFlow cluster. So it will open up the, they will launch the Spark executor, but inside each executor, they embed the TensorFlow parameter server and the worker server, and so that the training will start automatically. So this is the pretty much how we put the TensorFlow deep learning into our existing infrastructure for the data pipeline. So we are so this is kind of how we use a single cluster to host multiple open source components to support our end-to-end solution from backend analytics up to the user interface usage. So of course, because of time constraint, I cannot go deep into any one of the component, and I will be happy to answer any questions after the presentation. So next time, we head over the presentation to Jishin. We're going to conclude our presentation and open up for questions.
And yeah, thanks Shirley for the introduction here. And at the end, I just want to share some of the challenges we have experienced when developing such solution, and especially together with some of suggestions. So generally speaking, enterprise applications are very lagged behind than the consumer industries in terms of the adoption of the advanced machine learning technology. So there are some nature challenges there. One example is how to interpret and integrate the local context into the models. So like from our current experience, most of the big enterprise has its own unique characteristics. Like for example, how the network is deployed, what's the IT policy, what's the cloud usage policy. This is what we so-called a local context. So just because of local context, the behavior anomaly we're looking for can vary a lot from customer to customer. So we have, in our solution, we have developed this tool for the solution. On the left side, we have this continuous learning to keep updating the baseline, the normal baseline for the enterprise and each user in the enterprise from the input data. But in addition, the experience from, especially the knowledge from those experienced IT and security people in the enterprise is still very valuable complementary to any of the model. So for any of the analytics result, like alerts or anything we generate, we give user this one-click feedback loop. User can just tell us whether it's true positive or false positive based on their knowledge. Then based on the user feedback, we build some reinforcement learning to help the model convergency and adaptation to the local context here. So another challenge, actually pretty common challenge when you develop an enterprise application is lacking of training data. You know, the concern of collecting large amount of sensitive data is much higher on the enterprise side than the consumer industry. So in our solution, we build this kind of a hybrid or comprehensive analytics infrastructure. In the cloud, you can see we have this central training data repository, which contains all of the publicly and privately labeled training data. But meanwhile, we also collect the telemetry data and feedback from each of the customer deployment and send them to the cloud. And we actually group them based on different industry sectors here. So then when we retrain the model, we just combine this centralized training data with all these feedbacks and specific telemetry from each industry sector and train a slightly different model for each of them separately. So in this way, actually, we can, at least this approach helped us try to improve and also share the knowledge across different customers very quickly. And this pretty much ends up our talk, and I think this is, now we can go to the Q&A. Yes, please. Oh, sorry. No, over there, over there.
So a lot of what you talked about was based around detection, and I'm not very experienced in the security field, so please forgive my question if it's stupid. But what's the timescale that you're working on, and in what cases is it? I noticed that one of the tiers, tier 4, was large upload of data to a foreign server. So at what point is that too late to do anything about a potential intrusion? And is the earlier detection high enough confidence that you can take action before it's too late?
Yeah, very good question. Actually, in our system, as we discussed, briefly introduced before, we have a mix of different real-time and offline detection. This all depends on the behavior you're looking for. For example, the large upload. If the user really upload over 100 gigabytes data, even like just over 10 gigabytes, in a short period of time, we can almost do near real-time detection there, because just the signal is strong enough for us to have enough confidence to detect that. But to cover some of this sneaky behavior, as I explained, the user chop the data, all of this. So we actually, in our system, we developed a different frequency, like a detection, like from near real time to 1 minute, 10 minutes, 1 hour, even 1 day of the behavior. So that's the reason we can detect the combination of different kind of behavior anomalies there.
Thanks.
Yes. Oh. Or we can, yeah, well, I think we still have a couple more minutes.
So how do you deal with advanced persistent threats where they get into the system, they stay there for a while, and then they don't do anything, and then all of a sudden, for example, they upload the file to the cloud or wherever they want to do it. So there's a bunch of noise in between the initial signals that you got, but you didn't get a confidence score high enough to actually flag them as malicious until maybe you got the upload file. Is there something in your system that tracks this over that larger time scale without increasing the number of false positives that you get with that?
I try to repeat the question to make sure I understand. You are asking whether or what's our strategy to detect some of this kind of sequenced alert at some early stage?
Well, basically my question is, how is it that you detect things that are happening over multiple different time scales? So you could have a threat that happens over the course of weeks or months, but then intermediately you're going to have other events that are going to be false positive events. So how do you adequately track a malicious user over these long time periods without giving false positives in the near time?
Okay. Yeah, another good question. So there are many things we have tweaked or tuned in our system. So one way I can say is one thing maybe is related to your question is we actually have this we consider there can be multiple noise generated from each of the signal level. And if you just keep increasing score by looking at the different noise for each user, at the end, every user will become 100, right? So we actually consider of this time decay information. If you see one signal without the following signal, especially the expected next stage following signal, within certain time, each signal actually decay over time. So if in the case, if most of the signal we generate is the noise, and if there's no following like signals to conforming the previous one, those most of them will just finally will go to like 0 or very low score. That's one. And second to your question is, yeah, so we actually developed this, how to monitor this user's slow motion change to some like large change. How to handle that? We actually have this continuous behavior monitoring. When you see a signal, you try to decide whether you increase or reduce the score, use that recurrent network. So when you see a strong enough signal, the score will suddenly have a very large boost at the end.
Okay, thank
Yeah,
you for
maybe
your
one more
presentation.
question here.
Thank you for your presentation. We need to move
Oh, okay.
on.
Yeah, thanks everyone
so much.
for your time here.